Hello, I'm Renee San Miguel with the Georgia Tech College of Sciences. We continue our conversation with Paul Goldbart, outgoing Dean of the Georgia Tech College of Sciences, also the college's Betsy Middleton and John Clark Sutherland Chair. We taped this interview in February. With Paul's appointment as the next Dean of the College of Natural Sciences in the University of Texas at Austin, we've recast the interview as a two-part audio story serving as a valedictory for Paul, as well as a preview of our podcast, Science Matters, coming in summer 2018. We left off with a discussion of how College of Sciences researchers were part of a Nobel Prize-winning effort to confirm the existence of gravitational waves, something Einstein predicted 100 years ago. The first gravitational waves detected were the result of black holes colliding. It was a different kind of collision in summer 2017 that Tech's researchers heard and saw while working with LIGO, or the Laser Interferometer Gravitational Waves Observatories in Washington State and Louisiana. Here is School of Physics professor and LIGO deputy spokesperson Laura Cadenati speaking in a 2017 Georgia Tech video.
On August 17th, something special happened. For the first time, we detected gravitational waves that were coming not from the collision of black holes, but from the collision of two neutron stars. A neutron star is what's left after a star burns all of its fuel and implodes under its own weight. And this is going to give us important clues in where heavy elements are formed, how matter, as we know, is formed, in which processes. And this is very exciting because we are really making use of both the gravitational wave and the electromagnetic wave information to learn new things. We have really...
Again, here is College of Sciences Dean Paul Goldbart.
So if you take a cubic kilometer of Earth, it weighs about as much as a thimbleful of neutron star matter. So incredibly dense. I believe if you were to take the sun and have it become a neutron star, it would be about the size of the Georgia Tech campus. So incredibly dense matter and remarkable astrophysical objects. And every now and again, these are present in pairs out there in the cosmos, orbiting around one another. And in this event, two neutron stars rotated around one another, radiated out energy, and merged. And as they did in this cataclysmic eruption of merger, which is called a kilonova, that was where nature manufactures roughly half of the heavy elements. So if I look now as I am at my wedding ring, it has gold in it, and that, I believe, and that gold was almost certainly cooked, manufactured in through the collision of two neutron stars out there in the cosmos.
Tell me about some of the disciplines that are offering some exciting potential for scientists and researchers here at Georgia Tech. You talked about astrobiology. What other research are you wanting to keep an eye on here in the future?
Yes, let me tell you a little bit about neuroscience. Neuroengineering at Georgia Tech has been a growth field for a number of years and is doing very well. Has an international reputation, very strong. We have also begun to grow in neuroscience as opposed to neuroengineering, although as with many science and engineering disciplines, there's a great deal of overlap, a very soft zone separating them. So we're delighted, in fact, that we have a tremendously strong community of neuroengineers here at Georgia Tech. I'll tell you a short story. About 4 years ago or so, my colleagues in the College of Engineering dropped by the College of Sciences to say hello. I had been dean for a few months. And we sat down, they chatted, and they said we should have a neuroscience degree. And I thought about it for a little while, and I thought they're absolutely right. And I went to see Associate Dean David Collard, and we discussed the idea, and both of us agreed that this would be a marvelous step forward. Tremendous campus support, tremendous campus enthusiasm. We've been hiring neuroscience faculty to complement the neuroengineers and build a really thriving and broad community of neuro researchers here at Georgia Tech. Let me emphasize, that was not my idea. That was already running well before I became dean, and it's really been doing very well with great campus support. And the centerpiece of this step forward is the creation of a neuroscience bachelor's degree at Georgia Tech. And so until the summer of 2017, if one wanted to study neuroscience as an undergraduate, much as we would love to have you, Georgia Tech was not the place for you. It is now. And I have to say I'm tremendously excited, and we are finding that students are wildly enthusiastic about this new major. And it's actually quite a delight to construct a major after they have been constructed at other places, because you can look around and you can think and you can really focus on the future. So I think we've caught it just right. Great neuroscience, but also neurotechnology options built in, so that you really can train yourself as an undergraduate to be a neuroscientist of the future right here at Georgia Tech.
And it's my understanding you expected a certain amount of interest, but in the first year of the program, but you exceeded that.
We certainly did. We certainly did. So the numbers are somewhere like 150 students in the first cohort, and that is marvelous. And the more the merrier. Of course, growth like that brings the occasional strain, but those are the strains that every dean loves to have. So no complaints from me.
This is a problem you want. The name of the podcast is Science Matters. Tell me why all of the science and research that we've talked about here so far, why that matters. What's in it for all of us?
Yeah, so there's a tremendous amount in it for all of us. Let me start with the obvious. So the obvious is that science brings new understanding, and new understanding brings new capabilities and new power for humankind to control and work with and adapt and manipulate, ideally for sound, solid, good purposes, the world around us. And so science has given us tremendous opportunities to do that. I like to take the long sweep. I was at the dentist yesterday, and I was very fondly thinking of the folks who came up with anesthetics. And it's not very long ago. And so the same with vaccinations. Vaccinations are tremendously important. Let me take the example of weather forecasting. 100 years ago or so, catastrophic weather events in the city of Galveston, but all around the world and throughout history. We're now in a situation where we may not be able to forecast weather with the kind of provision that any naysayer might choose to impose, but the fact is we are saving human lives, we are saving property by the millions of people per year, and improving the human condition through that. Now, how does it come about? It doesn't come about just by focusing on weather. It comes about by a handshaking between all sorts of disciplines. So without the understanding that silicon, in fact, is a semiconductor, we wouldn't be in the situation of having solid-state circuitry and high-speed computers. And without beautiful ideas in applied mathematics, we wouldn't be in a position to make accurate solutions of the complex nonlinear equations that describe the patterns of weather. Without electromagnetics, we wouldn't have ultra-fast communications. And so this handshaking of the web of understanding of the way the world works comes together and helps move forward to really change the human condition. Of course, that happens perhaps nowhere more importantly than in the fields of medicine, where across the board one is confronted by examples in which it's scientific understanding that has provided one, not all, but one of the keys to forward progress. The example that I often like to cite is the laser. Lasers have had an amazing impact in eye surgery. I have friends who are ophthalmic surgeons, and they're brilliant, and I really appreciate them. But I don't think any of them would have come up with the laser. And so it's this handshaking, this relationship between the international web of science, international in space, but also going back in time, that has given humankind a sense of understanding, an ability to control, an ability to manipulate the world around us in terms of matter and energy that is incredibly empowering. But I want to take it one step further, if you don't mind, Renee. I would like to argue, and I believe this quite deeply, that although science is not in a position to solve all our problems by any means, there are complex cultural and social and political problems that are challenging and hard to address, and I wouldn't want to argue that all you need are scientists to address them by any means. But I do think that we provide a model for how to think about and make progress with complex problems. And I think the reason is that the scientific approach to problem solving has found a rather elegant and powerful balance between, on the one hand, reason, on the other hand, data, and on the other hand, third hand, creativity. And it's this kind of intersection between all three together with the ability to let go of ideas that no longer seem to work and happily move on, that I think gives science not only its power in its own domain, but also serves as a great exemplar to the way that we human beings can address some of the deepest and most challenging issues that we face in economics and in politics and public health, so forth. And I will also say that you may think of us, of we scientists, as people who sit and solve complex equations, and we do that from time to time. But actually what we really do is construct cartoon pictures of the way the world works in our heads or in our notebooks or on the chalkboard. And then what we do is we make what we call back-of-the-envelope estimates. We sit down and we just ponder and reflect and put together the different pieces of scientific understanding, and we make simple estimates. Do I need a field that has a strength of 1 Gauss to do this experiment, or do I need a field 1,000,000 times bigger? I need to know that before I consider the experiment or propose it to a funding agency. So what we do all the time is make these estimates, and we get a feel for things. And that way of thinking, I think, is enormously empowering. I'll call it semi-quantitative reasoning, and it's something that I think we really need to advertise and propagate out into the world. Just as an example, if I'm thinking about, let's say, a topic like employment, I need to have some feeling for the numbers. What fraction of people are out of work? What fraction of people are looking for work? How many new jobs were created over the past 8 years, for example? So one has to have a kind of framework, a kind of feeling for numbers and relationships between them before one really seriously enters into arguments. And that way one steered away from dogma and towards the light. And that, I think, is what science can help us do.
Given what you've just talked about here, since you've been here at the College of Sciences, what about your vision for the future here? How do you want to grow this college over the next, let's say, 5 years?
Yeah, so in my first 5 years or so as dean, we focused on many things, including strengthening the infrastructure under which people can undertake research, building up tremendous capabilities in nuclear magnetic resonance and mass spectrometry and other areas too. And I think that's been great. We've also built facilities that people share, and that creates community and promotes interaction. So I think we've supported the research endeavor with partnership with the campus well, and I'm pleased with that. We've also, I would say, we're beginning to figure out how to create the best platforms for early career scientists to learn how to navigate the complex web that is an academic life, rather than leaving them to their own devices, but also without a heavy hand so we don't too strongly influence the research that they choose to do. We're trying to find the middle ground to lift people up and really elevate the prospects for really great success. I think we've also had an impact on the scale and energy in the undergraduate programs. We're really in a marvelous partnership with the campus to increase the fraction of science majors and math majors at Georgia Tech from about 10%, aiming for something like 20%, just to give a kind of balance to the Georgia Tech community, and that's coming along, I think, really well. But looking forward to the next 5 years, I think for the college, one of the key objectives is to grow and strengthen the graduate programs. One of the reasons for this is that the reputation that we have worldwide, and the impact, more importantly, that we have worldwide, comes to a considerable degree from the quality and quantity of the research that we produce, and that signal is quite strongly carried by the people who we're fortunate to train. And so by having an even stronger and even larger graduate program, we will be sending out into the world these marvelously trained, exciting, thoughtful people who are carrying with them the Georgia Tech seal out into the scientific and mathematical worlds, and carrying our story with them. And so from my perspective, I think growing and strengthening the graduate programs is a key to our future success.
That was Paul Goldbart, Dean of the Georgia Tech College of Sciences until the end of July. In August, Paul will take the position of Dean of the College of Natural Sciences in the University of Texas at Austin. We wish him the best, and we thank him for his extraordinary work here in Midtown Atlanta. I'm Renee San Miguel with the Georgia Tech College of Sciences.